Great. Thank you, Bob. Delighted to be here. This is probably the fourth or fifth time that I've visited Stony Brook. Almost always this room. So I think today is the very first time I actually made it to the math department. So I'm glad to get to see that. So I understand that a number of you are potential visiting graduate students. This is a famous place. If I disappoint you in any way, that doesn't in any way reflect on the department. But I think it's a lovely place. It has a very long tradition. There are certainly many distinguished people in the audience that you can learn from. And so I hope this visit is useful for you. Great. This is a lecture called Can't You Just Feel the Moonshine? Does anybody know where those words come from? Close. Very close. One of my favorite songs of all time. This is James Taylor. I won't sing these words to you. I'll read them to you. And by reading them to you, you might actually recognize the song. In my mind, I'm going to Carolina. Can't you just see, can't you see the sunshine? Can't you just feel the moonshine? Ain't it just like a friend of mine? So on and so forth. I really like these words. And towards the end of the lecture, I'm actually going to use the words, can't you just feel the moonshine? Because it'll be an appropriate segue for the last part of this talk. Great. If you've never heard about moonshine, this talk will be good for you, because it turns out that the entire field of moonshine almost never happened. And I want to begin this lecture, which will be divided into three parts, where the first part is entirely historical. And what's interesting about the history of moonshine is that it reflects a very unusual set of accidents in the history of mathematics, where two completely different research programs came to a particular point in their work and found some numbers occurring in common, quite accidentally. And almost everything I'm going to talk about today can be traced back to those accidents. And so it's worthwhile then to remember that history. Then I'm going to talk about some more recent developments. Actually, the second topic I lectured on for the first time here a few years ago. It's an answer to a question of Witten on the distribution of black hole states when rephrased as a math and a number theory problem. And at the end, I'm going to tell you about what we're doing now in terms of moonshine, because quite frankly, I think that's, for many of us, represents some very exciting developments, which represents not only the third part of this talk, but the third phase of this subject. Okay. So to begin this talk, I said this begins with the history of two research programs. Well, one is the pursuit of the classification of the finite simple groups. As a graduate student at UCLA, I realized, as a beginning graduate student at UCLA, I quickly learned I really didn't know very much about finite simple groups. We had a professor named Richard Ellman who loved giving us crazy, difficult combinatorial problems about finite groups, such as classify all the finite groups of orders up to some large number, which was like 65 or 80, which at the time seemed like it might as well have been infinity. Now I can really look fondly back on those days, 20 years ago, because it all fits into the beginning of this talk. So the history of finite simple groups, you can say, goes back to the 1830s, thanks to Galois, who discovered the alternating groups and the finite simple groups PSL2FP. A few years later, Mathieu, if you don't know this name, he'll come up later. He finds his finite simple groups, the Mathieu groups. These are highly transitive groups on 11, 12 through 24 objects. They are all finite simple groups. They are large. And then by 1893, a mathematician that I didn't really know much about before preparing this talk, a mathematician by the name of Cole, who might be the Cole of the AMS Cole Prize, I honestly don't know, but he classified all the simple groups with order up to 660, and he did that in the 1890s, and I find that particularly impressive. Then there was a very long phase, which is like the first glory generation for in the theory of finite simple groups, populated by works by people like Brouwer, Burnside, Veit, all the way up through Thomson, beginning to cobble together what we now call the theory of finite groups. Through their works, Gorenstein assembled what was called the Gorenstein program, which had one goal, and the goal is to classify all finite simple groups. Very much like chemists today, and will probably forever, try to complete the classification of the periodic table of elements. So the Gorenstein program occupied about 10 years of mathematics. It was a very hot field in the 70s. And near the end of this program, there were a number of famous developments. One, the classification was completed. There is an end to the story. There is a complete classification of the finite simple groups. And along the way, one of the most important and fanciful events in this classification is the resolution of this conjecture revolving a group which was later called the monster by John Conway. So in the early 1970s, based on some combinatorial properties of other groups, Fisher and Bob Grice conjectured that there has to be an astronomical, absolutely gigantic, huge simple group, M, which they called the friendly giant, whose order happens to be this gigantic number. It's gigantic, but it's a number which is only divisible by very, very small primes. And in 1982, Bob actually constructs this group. It's not very easy to construct this group, and he later won, I think, one of these prizes. I think he won the AMS Steele Prize for this. He constructed the monster group, and it turns out to be an automorphism group of a 196,884 dimensional real vector space, which has additional algebra structure. In this talk, I'm going to put some numbers will be in red, and the numbers that are in red, you should be noted as being red, as somehow being special.
What does it mean that it's an explicit algebra?
He actually give you generators and relations. Yeah.
For this dimension in space?
Yes.
How many of those generators and relations?
I don't remember. Yeah. I'm not going to give you something out. Yeah, it's a lot. In fact, there are computational group theorists who are still trying to figure out efficient ways of computing this by embedding into like characteristic 2. It's not worth it for the purposes of this talk.
I think the address of finite simple group is short description of this.
Much shorter description. Right? But this is 1980. Yeah. So at the end of the day, the classification of finite simple groups almost fits on this slide. Namely, that the finite simple groups, apart from the natural infinite families, like the alternating series and the finite simple groups of Lie type, apart from them, there are 26 groups which are called sporadic. They're sporadic because they fall outside of this classification. And here's a network design of them. And what you can see is that the monster lives on top. All right, and I'm going to talk a little bit about some of these other groups later. What's important to notice is that most of these finite simple groups are somehow related to the monster, either as subgroups or as subquotients. And the groups, these are the ones that are circled in red, they've been termed by group theorists as being the monster's happy family. That distinction actually is going to be very important to us because some groups do not fall within this family, so they are truly sporadic, and they've been called the pariahs because they're not in the family. And the most famous of them, because it's been very difficult to get a handle on this group, is the Onan group, discovered, I think, in the late 1970s by Onan, who is still a professor, I think, at Rutgers. That's research program number 1. So let's just move on to research program number 2, which looks like it's not related at all. So it's the stuff of arithmetic algebraic geometry. We study objects called modular curves. So I want to just take a few minutes to give the flavor of why we study modular curves, because they're very exotic objects that encode lots of information that we're interested in. So as a toy model, the first kind of modular curve we study will be those that arise from actions of Möbius transformations in the upper half of the complex plane. So SL2Z acts on the upper half of the complex plane by linear fractional transformations. And for congruent subgroups of SL2Z, number theorists have for a very long time been interested in the quotients of the upper half plane by the action of these groups. These quotients can be assembled into compact Riemann surfaces by adding cusps. And the modular curves that I'm going to be speaking about all arise in this way for various choices of subgroups of SL2Z. To indicate why we care about this, let's study the simplest case where the subgroup we consider is the full modular group SL2Z. If you don't know it, it's not very hard to check. You'll learn it if you don't already know it. SL2Z is just generated by 2 matrices, one that represents translations by 1, one that represents inversion, tau goes to -1 over tau, And what the left-hand side begins to illustrate is the action of SL2Z on the upper half plane. The region that is shaded is a standard fundamental domain for the action of the upper half plane mod gamma. By adding the point at infinity, you can obtain a compact Riemann surface of genus 0, the Riemann sphere, by identifying the opposite vertical edges, the bottom pieces of the circle there, and tying it off at the top to get this modular curve.
You're always going to ignore the orbital structure.
This is all I'm doing in this lecture. Just trivially modding out and adding cusps. So this is what we call x01. It is genus 0. And what does that mean? That means that in the context of complex analytic functions or meromorphic functions, it means the field of functions on this Riemann surface is generated by a single function, one which we call the Haupt module. And there's a canonical choice for it, which is called J, which I'll tell you about right now. Before I do that, what do I mean by the term modular function? I just mean functions that are meromorphic, that are going to be invariant with respect to the Möbius transformations coming from the corresponding groups. And in the case of SL2Z, the generator of the function field is called J. If we demand and normalize it so it has a pole at infinity and has a vanishing constant term, which is what I will be doing throughout this talk, then you'll find that the Fourier expansion begins with these four terms. So what is Q? Q throughout is e to the 2 pi I tau, and the number in red, 1968884, I showed you before. Okay. All right, great. So very quickly, elliptic functions and curves. Elliptic functions give rise to the theory of elliptic curves first in complex analysis. So these are the standard facts. If lambda is a rank 2 lattice in C mod lambda is an elliptic curve. If we choose lattices so that they are normalized, so that they're generated by, say, 1 and a point tau in the upper half plane, then the value of the modular function at that tau will be an invariant. It's an isomorphism class invariant for the elliptic curve that has this analytic structure. And so in this way, number theorists have been using more refined versions of these two basic facts to do their work. And let me give you a number of instances of why this elementary fact very quickly leads to very deep information about elliptic curves. So what I've just said here is basically the statement that the modular curve x01 encodes isomorphism classes of elliptic curves. This statement is what drives a lot of number theory. If we replace SL2Z by other congruent subgroups, the corresponding modular curves still continue to encode isomorphism classes of elliptic curves, but it begins to encode them with extra structure. So for example, you may know about this very famous theorem of Barry-Mazur from the 1980s, where he was able to completely classify all the possible torsion points on elliptic curves defined over Q. This is complex analytic over C. Elliptic curves over Q are a much rarer breed. The rational points on them form finitely generated abelian groups, and as such, they're allowed to have some torsion points. What are the possible types of torsion points that you get? And there's only a finite set, and the theory that Barry developed for that is very important, and it begins with understanding the answer to the question of what are the rational points on these curves. And he was elected everything for that. And he won the National Medal of Science for working this out. It's a very, very deep area of mathematics. But even more recently, the proof of Fermat's last theorem also depends on studying these modular curves. I love this cartoon because it exists. So I wanted a very quick way of explaining another role in which these modular curves play a central role in modern number theory. And there's no better example of the utility of modular curves in modern number theory than, say, the proof of Fermat's last theorem. In one sentence, the proof of Fermat's last theorem relies on some observations of people like Fry and Ken Ribbit that said that if you could prove all elliptic curves are modular, then you can deduce that Fermat's last theorem is true. Well, in the mid-1990s, Taylor, together with his student Wiles, in a pair of papers that appeared in the Annals, proved most of this theorem, enough to prove Fermat's last theorem. It's now known to be true for all cases, thanks to works of a few other people in some loose end cases. But every elliptic curve over Q is modular. What does that mean? It means the following. It means every elliptic curve over Q, which whether you think of it as a Weierstrass model or in terms of pullbacks of what are called elliptic integrals, no matter how you think about them, every elliptic curve over Q can be found if you first start with the upper half of the complex plane, find a suitable congruent subgroup out of which you have a fundamental domain, which gives rise to basically your modular curve. And there are analytic maps, things like modular forms, that will map these points onto these elliptic curves in terms of this modular parameterization. So in this way, the upper half plane plays a central role in number theory in two ways. Above each point, you get models of elliptic curves by some generalization of what I described in terms of the J invariant. That's what all these elliptic curves up here represent. The ones in red are the ones that come from the fundamental domain, or maybe the ones in blue. No, the ones in red come from the fundamental domain. The ones in blue are just the repeats. But if you look at quotients of x0n, more precisely, if you look at factors of the Jacobian of x0n, you get a finite number of elliptic curves living below them, and that's what Taylor and Wiles proved. So in a very funny way, modding out the upper half plane by congruent subgroups tells us so much about elliptic curves. If you want to know the proof of Fermat's last theorem, or if you want to learn about quantities related to the Birch, Swinnert's, and Dyer conjecture, well, sometimes you're down here, and sometimes you're up here. And in the case of Birch, Swinnert's, and Dyer, you're both here and up here. Good. So I hope I've convinced you that modular curves are very important for us to study. So let's go back in time, the 1970s. What were people studying about modular curves at that time? They didn't know yet that this would be related to Fermat's last theorem, so they were actually asking much more basic fundamental questions. One of the questions is, classify all the modular curves that are hyperelliptic. And Andrew Ogg did that. And he wrote a paper in French. He's a very interesting guy. He's very California, but he wrote this paper in French. And in French, he wrote, x0n is hyperelliptic for exactly 19 values of n. There are exactly 19 congruent subgroups of a suitable type where the model of that curve could be written in hyperelliptic form. Why were number theorists enamored with this theorem? It's because of the following. It has an immediate consequence in terms of the arithmetic geometry of all elliptic curves. So to explain what that means, if I gave you an elliptic curve over characteristic P, so we could view it in its algebraic closure of Fp, it turns out that there are a finite set of isomorphism classes of elliptic curves over the closure for which the curves have no p torsion. Philosophically, it's easy to see why that should be rare. In the algebraic closure of a field, all expressions are supposed to be solvable, right? That's like the definition of algebraic closure. But in the context of the models of elliptic curves you choose, there are some for which it's literally impossible to find points of order p in characteristic p over the closure. And these are the curves which are called supersingular. The distribution of supersingular curves, the locus of supersingular curves, is very much a central theme in modern number theory, whether you study, for example, Katz's theory of p-adic modular forms, or if you study questions related to cryptography and trying to find models of suitable elliptic curves. Supersingular elliptic curves are all over the place. But back in 1974, there was a problem. And the problem was determine all the finite fields, Fp, for which every supersingular curve in characteristic P already lived at Fp. It means you didn't have to go to an extension to completely exhaust the list of supersingular curves. By the way, it's a famous fact that you never have to go beyond Fp squared to find them all, but the question is, when is it the case that every supersingular elliptic curve can be found by only studying congruences mod P? What Ogg's theorem says is this. It says that there is an answer, and the answer is that the finite set of primes are these primes because these are the primes that are related to the problem of understanding which modular curves are hyperelliptic. Determining when hyperelliptic curves when certain modular curves are hyperelliptic could be used as input to prove this corollary. Good. Maybe all of these primes should be in red, but they're not, but this is in red. And in the paper where Ogg proves this, he made the remark. I did take French in high school, but I wasn't very good at it, so I'm going to skip a lot of this. But it says that in January of 1975 at the Collège de France, Jacques Tits, who was one of the leading finite group theorists and representation theorists of the day, noted that the monster group, if anyone ever proves that it exists, happens to have order equal to this number, which I showed you before. And Og wanted to know, why is it that this set of primes is exactly the set of primes that divide the order of this group? That cannot be an accident. Of course, back then, if we were in the audience, we probably would have said, of course that could have been an accident. Because it's like just the product of like almost all the primes up to a certain point and they vanish. Okay. But fortunately, that didn't turn out to be right. It turned out to be quite brilliant. And I'd like to underline this in red because it says a bottle of Jack Daniels has been offered to anyone who offers an explanation for this coincidence. Some of us are still trying to collect. Although I don't drink Jack Daniels, but I still like saying that. Okay. If it were a bottle of nice French Côte d'Aron.
High school French, the spelling of values is wrong there.
Is that right?
It's EU, not UE. Same on the previous slide.
Oh, is that right? You know, I took a screenshot of Og's paper, so I have to defer to his. Oh, that's absolutely my fault. Yeah, I probably got a C in French. Yeah, okay, great. Well, that's the first glimpse of Moonshine, and so here's the second glimpse of Moonshine. I'm not sure what impresses you more. Probably the first glimpse of Moonshine is much more impressive, but my friend John Mackay, a few years after that lecture, comes up with this observation. This is actually the brilliant one. Why? Because it inspired John Thompson to look for more such relationships. So 196884 you've seen now earlier in the talk at least 2 times. And what it is, as I showed earlier, a coefficient of this modular function j. If you remember, and even if you don't remember, because I'm showing them, well, you can totally remember because here they are. The next 2 coefficients of the j function are there. And if you try to break it down as a sum of numbers that come from the monster, you can. What do I mean when I say numbers that come from the monster? The numbers on the right-hand side, each of those summands are irreducible dimensions of irreducible representations of the monster, which now we know exists. You might not be impressed because it's not very difficult to write integers as sums of numbers when you're allowed to include 1. All right, so I remember when I was a graduate student at UCLA hearing about Moonshine before Borchardt proved it, thinking, what's the big deal about adding up any set of infinite sequence of integers when I'm allowed to use 1? All right, if you're thinking that way, you're kind of a brat. I was a brat, but I'm going to fix that for you.
One-dimensional representation, or are they?
Yeah, it's all the trivial, yes. But I'll explain why it's. I think, in my opinion, is they should have addressed that much better back in the day, during like every talk they gave. They did, and let me explain how that works. So the coefficients of j are these numbers, and Thompson and later Serre made a longer list of accidents like this. So what are the numbers on the right? This monster group exists. There's 194 irreducible representations. If you evaluate them at the identity and take the dimension or the trace, that's what these chi's will represent, they're the characters, you get these 194 different numbers. And the conjecture that those numbers are suggesting is this, which we already just proved. What they really had in mind was much deeper. The conjecture is that there should be an infinite dimensional graded monster module, group module, called V natural, graded from -1 to infinity. So the nth component you should think of as being a finite linear combination of irreducibles with various multiplicities. And the claim is that the nth coefficient of the j function should be in order these modules. Well, there's infinitely many choices of modules that satisfy that because we have 1 at our disposal. So there must be more to it. And this is exactly what John Thompson had in mind. This is what makes the existence of this module far more striking. If you assume the conjecture, then for every element in the monster group, say G, you only need to choose 1 for every conjugacy class by definition. what you can do is you can define a formal power series or an analytic function on the upper half plane, if tau is the variable, called Tg, which is a sum over each of the graded components. But what we're going to do is we're going to take the trace of the image of the element g at the graded component and call that the coefficient of q to the n. There are 194 irreducible representations of the monster. So there are 194 different functions g. So you could ask, if this module exists with the property that the nth dimension is the nth coefficient of j, what else could we demand of all of the other 193 functions that makes it like j? And that's really what they had in mind. And this is the conjecture of monstrous moonshine. It is that for every one of these conjugacy classes, there is an explicit genus 0 congruent subgroup called gamma g. So remember, what it means to be genus 0 means the modular curve that is cut out by that has genus 0, so it has a Haupt module like j. And how would you compute the j, or the analog of j? You compute it because the representation theory of the monster just gave it to you. So as strange as it may sound, what the conjecture of monstrous moonshine is really saying is that it's saying that the right representation for the monster very strangely happens to be infinite dimensional, and it happens to be the one that's parameterized by a family of modular functions, which is somehow gluing together a bunch of different modular curves at once. This is a very hard conjecture. Now you worry less about having an arbitrary choice of ones, because there has to be this conspiracy, this collusion involving all of these functions. So in the early 1980s, Frenkel, Lapowski, and Merman basically prove a theorem that gives a construction for what should be the monster module. It's a specific vertex operator algebra that has the monster group as an automorphism group. Yeah.
In the conjecture, what does explicit mean?
Oh, very good. They have a table at the end of the paper where they give exact descriptions for generators for all these groups. That's not going to satisfy you. So let me tell you the one thing that will satisfy you. If G has order O, then this is going to be some extension of the congruent subgroup gamma 0 O together with some Atkin-Lehner involutions that come from the combinatorics of the group. So there's an explicit description for which group, congruent subgroup you get, and the most important invariant is what's the order of the element, and that's the level. So it's not like guess and check. Great. So Frenkel, Lapowski, and Merman, generalizing what they did with the Rogers-Ramanujan identities, which is another reason why I like to talk about this theorem, construct a candidate for this module. It's not effective. It's not really an effective calculation, as I'll describe in a moment. And I think, as most of you know, a few years later, Borchards, through his work, finally proves the monstrous moonshine conjecture, and he wins the Fields Medal for it. Great. So let's revisit the Jack Daniels problem, and then move on to the other two topics. I don't want to talk very much about the Jack Daniels problem, but because I raised it, I have to tell you something about it. One, now that we know that monstrous moonshine is true, you could ask three questions. And the three questions together, I think, merit the Jack Daniels bottle. So, question A, is it the case that if someone hands you an element of order P in the monster, that you already have a procedure for finding all the supersingular J invariants? Remember, the Jack Daniels problem was asking, is there a reason that the prime divisors of the order of the monster knows exactly which characteristics have a very simple description for supersingular elliptic curves? So is there a way to do that? And the answer is yes. And I'll explain that in a moment. It turns out that that answer was yes long before anyone knew about the monster group. Another question you could ask is, if P isn't one of those special primes that Ogg found, then why do you know a priori that there cannot be an element in the order of the monster? Does the geometry of modular curves tell you why there cannot be elements of certain orders in this group? Certainly, if you can't answer that question B, you don't deserve the Jack Daniels bottle. And lastly, if P is in the set, right, then why do we know that there's an element of order P in the group? If I gave you a set of elliptic curves, supersingular ones, and they're all defined over FP, and I can prove that there are no other ones, did I, in principle, actually give you a method for constructing an element of order P in that group? If I didn't do that, then we didn't really answer much of anything. So the answer to all these questions, you can do it. So question A, it turns out that very old work of Dwork already gave a procedure for finding all the supersingular J invariants by studying the Fourier expansion of J mod P. And it turns out that once you prove Moonshine, his procedure can be literally interpreted in terms of the group law of the monster, and they are directly in correspondence. And so it turns out that if people had taken the time to look at what Dwork had written down, I think people would have advanced much more quickly on Moonshine, because there are a lot of very important clues in the work of Dwork, which is, by the way, an important principle. When you work in a field, it always is a good idea to go back and read some of the papers that gave birth to a field. What is question B? Question B is, if I gave you, if there were no elements of order, if P wasn't an Ogg set, why is it the case that P doesn't divide the order of the group? Well, that's basically that's an immediate consequence of Borchard's theorem. Namely, by this recipe that I alluded to in Abinov's question, if I gave you a modular curve with positive genus, well, there can't be a Haupt module, and because there can't be a Haupt module, it doesn't even fall within the setting of Moonshine. So question B was answered by Borchard's. Question C is a little bit technical, but for people who think about it, let me tell you what the answer is. If P was on Ogg's list, why do I know there's an element of order P in the monster? And this is where it has to do with explicit construction. So I proved this with my new colleague John Duncan. Turns out that the following are true. You can prove that if P is an Ogg's list, then the Haupt module can be spanned by very, very special modular forms, p-adically, which are, let me just say, they're elementary theta functions. You can prove that. And if you think and study the proof of monstrous Moonshine, you'll realize that the calculations that go into these vertex operator algebras require that the spaces that are spanned by the Moonshine functions can only be spanned by elementary theta functions if there's an element of order P. And so there's a little bit of p-adic modular forms going on here, and I don't know. I think that's a nice conclusion to thinking about how one assembles these functions. Yeah.
What is meant by what are elementary theta functions?
Yeah, I don't really want to go into that. Right? All spaces of modular forms are generated by theta functions. So let me just say those that were defined by Hecke before people got into Brandt matrices. Okay. Okay. Great. So now let's get to the distribution of Moonshine, because this is now the topic that covers the work of the last maybe 8 or 9 years. So in 2007, Ed Witten and in another paper, Lee, Song, and Strominger, by the way, I think is a paper that's been cited 5,000 times. Didn't even know that was possible. But there's this paper by Lee, Song, and Strominger following up on this, on work of Witten, where this conjecture is posed. It's the vertex operator algebra, which is the incarnation of the Moonshine module, is dual to Witten's three-dimensional quantum gravity theory, and this is not my field, so I have to paraphrase. What this means is that there are 194 black hole states, and what Witten and others asked, but I'm paraphrasing it in this way, is how are the 194 black hole states distributed in this module? All right, so let me tell you what's going on. It's actually rather beautiful. It turns out that you don't need to know anything about black holes to formulate their problem. It's as simple as it gets. And you're probably already thinking it when I exhibited some of these summands in the first place. So the problem that Witten was asking is this. Mathematically, consider the Moonshine expressions that are afforded to us by the proof of monstrous Moonshine. Remember, 196884 is 1 plus 196883. All the coefficients of this J function are linear combinations of 194 different numbers uniquely with structure constants, non-negative integers we call the multiplicities, m, I of n. So you could ask, how many ones are there as n goes to infinity in each of these rows? How many 196883s are there all the way up to the very largest dimension? What is the makeup of this module? Believe it or not, by the late 80s, people weren't even sure when, like the 194th irreducible representation appeared for the first time. But they knew this thing existed. So let me give you some numerics. These numbers delta will refer to proportions. Delta will be the proportion of components that correspond to the trivial element. Delta of M2 is the proportion of summands that are the second element, all the way up through delta of 194. So each of these numbers added up to 1. So these two halves are just a statement that there's two summands, and one of them is 1, and one of them is the second one. So let me show you some data, which, by the way, was not easy to calculate. The 40th term in this module has very few ones in it. Out of all the terms, very, very few ones. And I hope you agree that that's good. If this module had lots of copies of the trivial representation, it would be, maybe we wouldn't give back Borchards its Fields Medal, but we wouldn't feel as good about having to use a lot of ones to assemble large integers. And look at this. There really aren't very many 196,883s either, proportionally. It's very low. And look at this. There are certainly a bunch of these the largest ones. Anyone want to make a conjecture? Okay. Let's go to the 60th one. Look, the proportion of ones is even smaller. Is that going to 0? Going from there to there, right? Just going from the 40th term to the 60th, the proportion of ones is almost like 0. And very good. We have a winner. And over here, the largest one occurs about 4.4% of the time. We have a winner. So thank you. So by the 140th term, the proportion of ones is still shrinking, but not shrinking as quickly. The proportion of 196,883s is still shrinking, but not as quickly. And the 194th one really has stabilized. And in fact, if we keep going, by 240, you see a pattern, and it's what he was guessing. This is asymptotically a regular representation, which is nice. The Moonshine module is doing its very best to have an asymptotic distribution, which is regular. What does that mean? It means this. It means for each of the 194 irreducible representations, asymptotically, the multiplicity of the ith component at grade n is given by this asymptotic expression. What you notice on the right is that all of the ugly stuff in no way depends on which representation you're taking. The only dependence on which one you're taking is in the dimension itself, which is what he's saying. And so what that tells you is that, as I said, this is asymptotically regular. And so as n goes to infinity, the proportion of the multiplicities of the ith component is really just a dimension of the ith component compared to the sum of all the components. It's actually very beautiful because you might ask about what about secondary terms, third terms, and those are not regular. If you're familiar with problems like the Weil conjectures, there are Weil conjectures relating to growths and error terms of the subsequent terms. Only in its first approximation is this module regular. Great. So that was our okay, so I'm going to skip the proofs. Okay, because I want to spend the rest of it talking on the new Moonshine. Let me just say, if you work in analytic number theory and you learn enough, there's a subject called Kloostermania, basically populated by important works by people like Sarnak, Ivaniech, and the like. And if you spruce them up in the right way so that they could be applied to Moonshine, we have the technology to prove those theorems. And that's not the point of this lecture. Great. So to conclude, in the last 15 minutes or so, I need to tell you about the new work because, like I said, this is where I think, which I'm quite excited about. In fact, Nature, the magazine Nature, which I never thought published papers about mathematics at all, has invited us to write a paper about mathematics. They may still reject it because they are objecting to how we write papers. The editors, very funny story, if you write the word proofs in your paper, they'll send it back for revision because they want to know about methods. But if you write down a rigorous proof, that's too much. So I don't know what the future of publishing with Nature is going to be, because if you can have an incomplete proof, but it's like satisfies methods, maybe get published in Nature and get rejected by every math journal. I probably shouldn't have said any of what I just said, but it's an interesting thing. Springer and Nature have recently merged I do a lot of work for Springer for their journals. So this issue has actually arisen. How does a journal like Nature begin to publish science that is mathematics when they have no tradition for doing it? So wish us luck. So I want to end by talking about new moonshine, and I'm going to talk about it in two phases. The first part occurred here at the Steinman Center. In 2010, we had a workshop on string theory and moonshine, and three distinguished Japanese mathematicians, Eguchi, Oguri, and Tachikawa, had read one of my papers in the AMS notices, did some calculations with the K3 surface elliptic genus that they were studying, a specialization of it, and they said, we found this Mach modular form in your paper that begins with these Q coefficients. I'll say in a few words later what a Mach modular form is. And they noted that the Mathieu group, M24, this is the largest of the simple sporadic groups that were found by Mathieu, its character table reveals these irreducible dimensions. And the numbers in red are among the coefficients of this function they found in their work. Well, shortly after they announced this, Terry Gannon proved that there is an infinite dimensional M24 module which satisfies moonshine, exactly the same sort of phenomena I've described. Those functions that I called TG earlier were the functions defined by Thompson. We now refer to them as Mackay-Thompson series. So just an analogy with the monster group, for the Mathieu group M24, there is moonshine. But the moonshine is different. Instead of using modular functions, it uses what are called Mach modular forms. They're somewhat related, and let me tell you how they're related. So throughout, tau represents a variable in the upper half plane with real and imaginary parts x and y. For every real number k, there's a hyperbolic Laplacian operator that are used to annihilate forms, usually holomorphic forms on modular curves. And a harmonic Moss form is one of these guys. If you have a real number k and a congruent subgroup, say, of SL2Z, then any real analytic function, say m, from h to c, will be a harmonic Moss form if, 1, it behaves in a nice way with respect to the Möbius transformations. The role of the weight here is now here. For modular functions, the weight is 0. And to be harmonic means that it's, well, harmonic. It's annihilated by the Laplacian operator. There's other conditions, but let me not go into that. These are generalizations of modular forms. Any holomorphic function is, of course, annihilated by the Laplacian operator. But what's interesting about the Mach modular forms is they cut out a space of real analytic functions that contain in the corner a very small part, the classical modular forms we study. They're very, very small. There are many, many more of these harmonic functions than are ordinary modular forms. And what Gannon proved is that moonshine for the Mathieu group involves this enlarged set of functions. Shameless plug. I have a book coming out in June. Please buy it. Make sure your library buys it. I'm working really hard on it. I want someone to read it. So it'll appear in the AMS Colloquium series. And so if you want to learn more about the subject, that's the cover. And in terms of Fourier expansions, well, that's what I need to explain in terms to explain the connection to the Mach modular forms. Well, it turns out that every one of these harmonic Moss forms has a Fourier expansion, but now it has two parts. If gamma AX is the ordinary incomplete gamma function, so that's the gamma function where you forget to integrate until you get to this point. This function has a Fourier expansion, one part which is holomorphic, and the other part which is almost holomorphic, namely in that the only thing that's preventing it from being holomorphic is the dependence on the imaginary part of tau right here. What is a Mach modular form? The Mach modular form is this part for those functions where this is non-trivial. Okay, so the Mackay-Thompson series for the Mathieu 24 group are all functions like this, that part of these harmonic Moss forms. This is a picture of me. I want to say where the terms Mach modular forms come from. It comes from a letter that we're very grateful actually survived. There's a famous Indian mathematician. I hope most of you know his story. If not, I know a movie you could watch. It's a letter that Ramanujan wrote 3 months before he died. He wrote it from his deathbed, and the letter begins with the words, "I'm extremely sorry for not writing you a single letter up to now, but I've discovered interesting functions recently which I call Mach theta functions, and they enter into mathematics as beautifully as the ordinary theta functions." The functions that Gannon used were in this letter. So there is no solution to the physics problem of the Japanese mathematicians without the receipt of this letter. If this letter had been lost, we wouldn't know where to look. It's crazy. So the new moonshine, it seemed to be related to things like what the Japanese physicists found. So what did they find? Well, they found that moonshine seemed to be related to 24-dimensional unimodular positive definite lattices. So the monster is doing its very best to be the automorphism group of the Leech lattice. That's not quite true. It's the double cover of the automorphism group of the Leech lattice, but that's enough for me to say that this is true. The M24 group is the automorphism group for another rank 24 lattice called A124 in the ADE scheme of classification of root systems. So you could ask, does moonshine live at the level of rank 24 lattices? Well, that's what Miranda Cheng, John Duncan, and Jeff Harvey conjectured here in this room. Let's let L be an even unimodular positive definite rank 24 lattice. Let X be its root system. Let W be its Weyl group, basically the set of all symmetries of the root system. If you don't know what that means, this is just all the kind of language that's required to identify these lattices. Then there's a group called the umbral group, which is the automorphism group of the lattice modded out by these symmetries. And they claim that there is a moonshine for each one of these groups. Namely, for each one of these groups, there's an infinite dimensional G module, where G is basically the automorphism group of this lattice, satisfying the kinds of conditions that I've described for you in this lecture. And more importantly, apart from the case of the monster, which is what I'm calling the Leech case, the Mackay-Thompson series all turn out to be these Mach modular forms in the sense of Ramanujan, the holomorphic parts of Moss forms, harmonic Moss forms. So we proved that was true, announced that here, and I think the Simon Center even wrote a story about it in the Quantum magazine after we did this. In the case of M12, again, some of these series were found in Ramanujan's deathbed letter. So we would be lost. I almost said something very bad. We would have been lost had he not died. Of course he died. We would have been lost had his deathbed letter not gotten to us, because these are some of those functions. It's crazy. The representation theory for some of these gigantic groups were embedded in letters that Ramanujan wrote before anyone knew that there was even such a thing called a vertex operator algebra or any of this stuff. So up to about a year ago, I thought this was going to be nearing the limit of moonshine for us. And I'm so glad that we thought about it and discovered that we were wrong. So here's the slide. Can't we just feel the moonshine? So now moonshine is largely understood for the monster, of course, through Borchard's work, and in the happy family. Right? You know how to retrieve the character table for groups which are, for example, subgroups of large groups. Moonshine is also understood for these umbral groups. So if you understand the automorphisms of rank 24 lattices, you're really talking about representation theory of some groups. But is there more out there? Well, so the last question in the seminal paper raised by John Conway and Simon Norton on the subject is this. They had done lots of numerical experiments, and their numerical experiments revealed a lot of clues that are certainly related to this first bullet item. But what they never found evidence for, and Borchard's also raised this as the last problem in his ICM lecture, and the problem is this. We ask whether the sporadic simple groups that may not be involved in the monster, keeping in mind the monster had not yet been constructed in 1979, is there moonshine for any of them? And these were the groups in the finite classification that I did not circle in red. These are the groups which are called the pariahs. Is there moonshine for all of these groups, and where does it live? So in the very last few minutes, let me tell you what we proved. We figured it out. So I'm going to explain our results for the case of the Onan group. This is a finite simple sporadic group of this order. It lives outside the happy family. And in 1976, that was like a theorem. People proved theorems that said these groups are not related to the right. That was like a theorem. So one example of the theorem we proved is this. The first part won't come as a surprise. There is an infinite dimensional graded ON module, ON for Onan, and its Mackay-Thompson series are modular. They're not weight 1/2 now. They are weight 3/2 Mach modular forms, meaning that they're holomorphic parts of these harmonic Moss forms of weight 3/2. Now, the thing about weight 3/2 and the theory of modular forms really is exciting. If you've heard about big works of Gross and Zagier in the 1980s, they are all statements about weight 3/2 modular forms, right, Abhinav? So Abhinav's probably getting a sense of where I might be going with this. So let me tell you, that's totally true. So it turns out that this infinite graded module W has the property that its dimensions are simple formulas in objects that people like Serre, Gross, and Zagier have been studying for a long time. They're arithmetic in origin. So in a phrase, the dimension of these modules are traces of algebraic numbers. And what are they traces of? Discriminant minus n values of a modular function called J2. It's a very natural one. What does that mean? Some of you may have seen the funny observation of Ramanujan that e to the pi root 163 is very nearly an integer. Well, if you make it an integer, the dimension of the 163rd component is this polynomial in that integer. J2 literally is going to be a quadratic polynomial in these traces, and the quadratic polynomial, you can see this is the constant term. This is universal. What does that mean? If you gave me a discriminant and you found all the CM points of that discriminant and plugged in for x here and here into this quadratic polynomial in sum, that literally is what this graded dimension is. These are polynomials that you would want to know how to calculate if you do the inverse Galois problem for the corresponding abelian extensions of the corresponding imaginary quadratic fields. These are extraordinary series because it turns out that the arithmetic of all of the representation theory, without any exception, can be written in terms of linear combinations of the following gadgets. They are linear combinations of the famous class numbers of Gauss. They are linear combinations of singular moduli, numbers of the type I just showed you a moment ago, and L values of modular elliptic curves and L values of this abelian surface, this genus 2 abelian surface. There is no ambiguity in terms of computing the graded traces of this module because every part of it is completely arithmetic geometric in origin. Because of that, it must tell you that this module informs us about the number theory. See, one of the things I always wanted is if you prove Moonshine, does the representation theory or does the number theory get better informed because you've proved a correspondence? We have too many instances in mathematics where we relate two things that are both hard, and we're very excited because we've related two things that are both hard, but we haven't learned a new thing about either side because we've worked hard, except the relationship. This is the first instance in Moonshine where we've clearly learned something new about the number theory because the representation theory informs it. So, slide 1 says, the module sees class groups. It turns out that the dimension of this module, mod 16, gives us the class number. It turns out that if P is inert in the corresponding quadratic fields, then the dth dimension sees the 3 and the P part of the class number. So for the primes that divide the order of the Onan group, you can compute P parts of class groups under certain inertia conditions universally with this single module. Does it see elements in Selmer groups and Tate-Shafarevich groups? So if you know about something called the Birch-Swinnerton-Dyer conjecture, or perhaps the recent work of people like Manjul Bhargava, in number theory, we're absolutely interested in studying ranks of elliptic curves. We're absolutely interested in studying how you compute quantities related to the Birch-Swinnerton-Dyer conjecture. This module does it. So suppose that E14 is the modular curve x014, and or is the elliptic curve x015. Every one of them can be twisted by an infinite family of quadratic characters, so that's what we do. Let's factorize 14 and 15 as p times p prime in an obvious way, 2 times 7 and 3 times 5. And then under these Heegner hypotheses, we can prove unconditionally that the trace of an element of order p prime sees an element in the Selmer group if and only if the trace thinks it's looking at a class group. The Selmer group is non-trivial if and only if the element of it sees an element of order p, which is the complementary factor to p prime, It sees an element of order P if and only if the element of order P prime thinks that the dth component is a class group. That sounds like the Burchard-Swinnerton-Dyer conjecture. You have a point on an elliptic curve if an L value is 0. 0 cannot be distinguished from anything because it's 0. This is the p-adic, pardon me, the p-adic incarnation of that. Similarly, if we have a little bit of extra information, if the L value of your elliptic curve isn't 0, which by Burchard-Swinnerton-Dyer, and actually is a theorem of Colli-Vagen, means the elliptic curve has rank 0, then our module can produce and guarantees the existence of elements of order P in the Shafirevich-Tate group unconditionally if and only if the P prime trace of that component thinks it's only looking at a class group. All right. So this theorem will be used very soon to set world records on ranks of elliptic curves in these families of quadratic twists and world records on counting elements of order P in the Shafirevich-Tate groups of these curves. So that's actually, I think, very exciting because if you study number theory, you can spend your whole life studying like theorems like one of those bullet items. So to come to a conclusion, you could ask, so what really in the world is moonshine? So I think I can paraphrase what moonshine really is. Moonshine is this. It's not what everyone thought it was, even up to about 10 years ago. It's a very precise phenomenon. Moonshine is a principle that organizes divisors on products of modular curves. What are the modular curves that arise in moonshine? They are the ones whose levels are orders of elements in the group that you are studying, without exception. How does it organize the divisors on these curves? Well, this is where the answer is it depends on the weight of the forms you're studying. So for every group for which there is moonshine, there is going to be the following. There exists an infinite dimensional G module. Moonshine means that infinite dimensional G module comes along and is equipped with a finite set of automorphic forms, one for each conjugacy class. So G represents a representative for each class. So when I said that moonshine organizes special divisors, the question is what divisor information is this family of modular forms organizing? What's organizing this? This finite set of forms we should view as being in the direct sum over the conjugacy class of this group of these products, the products of certain spaces of modular forms with the Jacobians whose levels are the orders of these elements. So now the question is, what divisors are we getting? If the weight is 0, you get the most uninteresting divisor in the universe. It's minus infinity plus a number. That's the help module. The help module is a generator of the modular function field that has a simple pole at infinity, constant term 0. That's like just saying, find me the polynomial x minus 5 if I told you it had degree 1. It's not exciting. But in weight 1/2, in umbral moonshine, what do we get? We get this theory of Heegner divisors. For every Heegner divisor, you get a class. And what do we get in weight 3/2? You get the sum vertically over all the discriminants. So moonshine lives at every weight, and it's really just a question of how you organize divisors on the module. These curves don't move. So for number theorists, if you're interested in when a curve has genus 0, well, that was easy. Og did that. If you're now interested in finding points of infinite order on elliptic curves, you go to moonshine and you study the weight 3/2 functions and you look for the conditions that I was describing. If you want to study growth of class numbers or explicit class field theory, you go to weight 1/2 and look at the minimal field of definitions of those divisors. So I'm actually very excited about that. I'm not sure that everyone will be, but I assure you that for each one of those different levels, there have been people who have devoted their entire careers to that. And you'll see over the next couple of years that some famous theorems will be reproved very quickly by saying there's an element of order 5 in this group, and then boom, that's just finished. Because the representation theory now informs the number theory. I like that. So it was very important to me. If you prove moonshine, what have you proved? In this case, I'm happy to offer that we proved something about number theory that we didn't know before because we worked hard to do it. So what's the evidence? And this is what I was saying. For monstrous moonshine, it was boring. Minus infinity plus a point. That's like the least interesting divisor in the universe. Umbral, much more interesting. Now for groups like Onan, the pariah, we're packaging this vertically, and that's what people like Gross and Zagier and others in the 80s began to recognize the point of. And rather nicely, weight 3 halves encapsulates their works as the first examples. Great, so that's all I wanted to talk about. Thank you. Questions? Yes?
So in this answer to the Jack Daniels question, there was an explanation in terms of representation theory of when a certain prime was divided the order.
Yeah, yeah.
Is there a similar explanation for why the particular exponents occur?
Great question. I don't know how to answer it. Yeah, I've been asking that for myself for a long time. That's a great question. I don't have an answer. Yeah. I'd love to have an answer to that. Yeah.
Control the weight here.
I can. This is, oh, here? Well, I can control the weight because I know all the lists. If you have a finite set of things, you can control the weight because it's a finite set. So I can control the weight here in the sense that moonshine has only been proven in weight 0, 1/2, and 3/2. In every instance where that holds, this is exactly what happens. So there is moonshine coming, for example, for Shimura varieties. We know about what are called traces of singular moduli, and it'll be like an analog of weight 1/2. So I think the real direction is how do we replace modular curves? And we know how to do that. We haven't, so that's that's ongoing research. So the finite simple groups will live at the level of Shimura varieties and Shimura curves. Is quite right, but yeah.
So the monster group is like the automorphism group of some algebraic structure on a very large dimensional vector.
Yes.
And then you said the first non-trivial irreducible representation has dimension 1 less than that.
Yes.
So
there's a
the representation given by the automorphisms has a codimension 1.
That's right. Exactly. Yeah.
So is there some intuition for what the codimension 1 subspace is?
Well, I mean, there's lots of ways. I mean, I can explicitly give it to you. I mean, I don't want to make it sound fancy when it's you point in that direction and that's it. I mean, it's like, Yes.
Is there any example known of non-sporadic?
Oh, easy. That's actually very easy. I can even do. Well. That's a good, So you could do this. So how do you can actually just produce lots of moonshines in the following way. I haven't done this, but it will work. So take 5 different modular functions, one with level 1 and 4 with other various levels, pretty small orders, and pretend that they are the trace functions for some group, corresponding elements, da-da-da-da. Find groups with low orders, maybe like elementary abelian or whatever, okay? Work through the Schur orthogonality relations and literally just try to solve for the multiplicities of each of the components in those Q series. You just need to know that they're integral and non-negative. So if you have sufficient exponential growth, which a pole would guarantee, then it's just a finite number of congruences. And if the numbers are small enough, we should be able to cook it up so that the congruences are satisfied.
What I meant was in the other direction.
Suppose
take
okay.
An AN or an SN. Yeah, let's take an AN for some larger chain, let's say.
Like 5?
Yeah.
Yeah. Yeah. Yeah.
And then, is there is there an example of natural interdimensional module for which you can get similar sort of modular?
Yeah, for many of them, absolutely there are. So in fact, many of the umbral groups would be like that. I don't remember if A5 is one of them. I think S4 is in there. Yeah. Yeah, so early on, people thought moonshine was about finding exotic groups. It's really not. It's really a principle of how the representation, orthogonality relations for the character table are encoded with divisors and the theory of congruences for modular forms, as I think you can imagine from what I'm saying. That's really what this is. When is a linear algebra of representation theory compatible with the theory of congruences of modular forms, which we now know so well? That is if and only if for moonshine. And that's where this comes from. Yeah. Oh, yeah, okay.
You had this theorem where the list of all, where you had this finite frames, you could show that that was the same as the list of frames for which you had these p-adic
Ah, yeah, yeah,
So the question is,
yeah.
is that proof a natural proof in the sense of, you know, or is it so here's what a
Yeah.
natural proof would be. You would say, okay, I can characterize all the primes for which the theta functions are stand, and then that coincides
Yeah.
with this list. On
Yeah.
the other hand, a natural proof would be, you know, for some arithmetic geometric reason, this equals that.
Yeah, no, no. That's so, yeah. So when I say, I think I even put quotes around that slide somewhere. I fully admit that the proof I offered for that question would be far more acceptable to someone who is familiar with modular forms than someone who is coming from group theory, right? So no, I think that literally depends on. So it'd be interesting to see what you think. You know, it's a question. So what side? If you had to vote, yeah, you know, maybe you're liberal or probably not Freedom Caucus or whatever, but at the very least, you can argue that being able to be spanned by elementary theta functions is a third condition which produces the same set of primes. That we can all agree on. Great, perfect. Yeah. Yeah.